This is example 6.11 on page 234 of your textbook, and this is another example utilizing the concept of collecting gases over water. So this is a two-part process. In the first step, we're going to need to determine the dry gas pressure by subtracting out the partial pressure of water. And then in our second part, we are going to need to plug in our dry pressure as well as some of the other variables into our ideal gas law equation to solve for our variable. So the question states that in order to determine the rate of photosynthesis, oxygen is emitted by an aquatic plant and it's collected over water at a temperature of 293 Kelvin or 20 degrees Celsius and a total pressure of 755.2 millimeters of mercury. Now, over a specific time, a total of 1.02 liters of gas is collected. So they want us to find the mass of oxygen in grams that forms during this photosynthesis reaction over this specific amount of time. So like I said, our first step to ultimately solve for the mass of oxygen that is produced is to determine just the pressure of the dry gas. And by dry, it just means it doesn't have water vapor partial pressure mixed in. So we're going to utilize the concept of Dalton's law of partial pressures again to say that our total pressure of our vessel is equal to the partial pressure of oxygen plus the partial pressure of water. And in the problem, it states that we have a total pressure of 755.2 millimeters of mercury. It also states that we are collecting our gas over water at 20 degrees Celsius. So I can go over to my vapor pressure of water table and figure out that water's partial pressure at 20 degrees Celsius is 17.55. So I have two variables. I have my total pressure, which is 755.2 millimeters of mercury, is equal to the partial pressure of oxygen plus the partial pressure of water at this temperature, which is 17.55 millimeters of mercury. So if I subtract out my water vapor pressure from both sides, I'm going to be left with just the pressure of my dry H2O. So pressure of oxygen, in this case without any extra added partial pressures, is 737.65 millimeters of mercury. So now that I have my pressure of oxygen with no extra things added into it, I'm going to start looking at step 2 of this calculation, which is to use the ideal gas law to solve for moles of oxygen, and then from there, after that, we can convert moles of oxygen into grams of oxygen by using the molar mass. So on this second slide, I have written my solved for partial pressure of oxygen. That's what we just solved for in this previous step. And now I'm going to read the problem again and make sure that I have all of the other information that's given. So it gives me a temperature in Kelvin, 293 K. It gives me pressure, which I utilized previously. It gives me a volume, 1.02 liters. And the only thing that we have left that we're going to be solving for is our moles of oxygen. We always have our ideal gas constant, which is 0.08206 liters times atmospheres over moles times Kelvin. So before we plug into the ideal gas equation, the partial pressure of oxygen that I calculated, I need to convert that into atmospheres in order to plug in and utilize the ideal gas constant that I want to. So I'm going to divide by 760 millimeters of mercury, 1 atmosphere on top, and that's going to give me a pressure of oxygen of 0.97059 atmospheres. So now I'm ready to plug into my ideal gas law equation. So my pressure, 0.97059 atm, my volume, 1.02 liters, is equal to N, which is what I'm looking for, times R, which is 0.08206 liters times atmospheres over moles times Kelvin. And I'm also multiplying by temperature, which is 293 K. I just ran out of room, so I wrote it underneath. So now, if I divide both sides by my gas constant, 0.08206 liters times atmospheres over moles times Kelvin, and by 293 K, there we go, moles times Kelvin. Atmospheres will cancel, liters will cancel, Kelvin will cancel. I'll be left in units of moles, which is what I'm looking for. So currently, after rearranging and solving the ideal gas law equation, I get that my mole amount is 0.041175 moles of oxygen. Now I'm not quite done with this problem because it states that it wants the mass of oxygen in grams that forms. So to convert from moles to grams, I need to multiply by oxygen's molar mass. So O2, if I look on the periodic table, the molar mass of oxygen by itself is 16. I need to multiply that by 2 because gaseous oxygen exists as O2. So my conversion is going to be my moles of oxygen divided by 1 mole O2, and on top, 32 grams oxygen. Moles cancel, and I'm left with grams. So that means my mass of O2 produced is equal to 1.32 grams of oxygen. So all of that work utilizing both Dalton's law of partial pressures and the ideal gas law to calculate the mass of oxygen produced during photosynthesis of this aquatic plant.